I'm Max Grossman from 7POD Technologies, and I'm presenting the solution to Challenge 2 on behalf of Nav Ravindranath, who is a applied math master's student at Columbia University. In this challenge, we're looking at factors that relate to the energy, the electricity, and the gas consumption of buildings in downtown Chicago. We can see in the plots on the screen right now that electricity and gas consumption both vary widely across the span of a single year. In particular, we see lower energy consumptions in the summer, in the warmer months, and higher energy consumption in the winter, particularly of gas. However, this isn't a simple relationship. We can see spikes that are uncharacteristic for a particular time of the year, indicating that localized weather patterns or other features are causing nonlinearities or anomalies. And so complex modeling is required in order to accurately predict electricity and gas consumption. So in this project, what we did was we built a model in this Jupyter notebook to predict electricity and gas consumption on an hourly basis per building based on factors such as building size, outdoor temperature measurements, indoor temperature, and indoor humidity. The first step of this process was lots of data wrangling and preprocessing. Probably the most interesting part of this stage was co-locating points on the building grid and the weather grid. So the weather grid and the building grid in this data set are disjoint in that the points at which these measurements are taken differ, even though they are correlated with the same geographic location. So what we did in this solution was we built a KD tree out of the weather data points, and then in order to find the local weather for a particular building, we use that KD tree to query for an approximation of the weather at a building's centroid. And this way we're able to align these two grids. With that, the next step was to kind of select our independent and dependent variables. So you can see here we're pulling out factors, independent factors such as the height of a building, the number of floors in the building, its location, the time of day, outdoor air temperature, indoor humidity, and then we're going to be relating those to our dependent variables, which is electricity and gas consumption on an hourly basis. We use these to construct both a training and a test data set, and then we tried three different types of models. A linear, a k-nearest neighbors, and an MLP, a regressor, which is a simple form of neural net with 3 hidden layers. We print out the R-squared scores here. We can see that the linear regressor doesn't really capture much of the complexity with only an R-squared score of 0.38. The k-nearest neighbors performs much better with an R-squared score of 0.90, but the MLP regressor, the simple neural net, performs the best with an R-squared score of 0.92. We hope that these results can be leveraged by individual organizations in order to better anticipate their energy requirements, but even more importantly, by city and states such that they can more efficiently use the grid, better understand energy storage requirements, integrate green energy resources into the grid, and of course motivate the construction of greener buildings.